G'day viewers. In this segment we'll talk about retransmissions as a strategy for handling errors. Okay, so just as a bit of context, we have two general strategies which we'll use to correct errors in networks. The first strategy is to detect that an error has occurred, say with an error detecting code, and then retransmit the information across the network. We've already seen the error detecting code, so now we're going to focus on the retransmission half of this strategy. The overall strategy goes by the name of ARQ, somewhat archaic name, it just stands for Automatic Repeat Request, but we can just think of it as retransmissions. The second strategy is to correct errors with an error correcting code. Send enough information as part of the message that the structure can be checked and any errors that occur along the way can be corrected. We've already looked at how this strategy works as part of our exploration of the link layer. And I'll give you just a little bit of context on reliability in general before we jump into retransmissions. An important question for us to consider is where in the stack we should put reliability functions. Well, we have a whole stack here. Should our reliability functions for dealing with errors go at the physical layer, the link layer, the network layer, the transport layer, or the application layer? What do you reckon? 5 different choices. The answer is essentially that reliability functionality should go everywhere in the stack. Reliability is one of those key issues for networks. Networks have to be able to deliver information reliably. And to support that, each layer will do its part. The key issue here really is how each different layer should contribute to the overall reliability. What we will find is that at the low layers of the protocol stack, like the physical layer, error handling functionality will mostly be there to mask errors, as we saw with an error correcting code. This is often as a performance optimization. Looking at retransmissions at the link layer is again about masking errors. If the retransmissions occur as in Wi-Fi, the higher layers, like TCP, will never know that there's been a loss. They won't have to worry about it. The error will be masked, and this will generally improve performance. On the other hand, all the protections we like at the low layers won't stop things going wrong at the higher layers. Maybe a sending application can't connect to the right receiving application, can't find the right path through the network, or a message is received which is unexpected on the other side. No amount of scrubbing the bits as they go over to detect and correct any transmission errors will handle these scenarios. So the higher layers of the protocols will also need their own functionality to handle reliability. This functionality is mostly then concerned with correctness and usually recovery actions rather than performance and masking errors. Okay, so that's reliability in general. Let's go on to ARQ. ARQ is used in Wi-Fi, and we'll also see it in TCP. It's used where errors are expected or they're common enough and they need to be corrected. In Wi-Fi, it's because it's wireless and there's a lot of loss, so packets might be lost. In TCP, it's because packets might be lost in the network due to congestion. We'll cover TCP later. Now we're really just talking about the link layer, but much the same mechanism is used. The rules for ARQ are fairly simple. At the receiver, all you have to do is automatically acknowledge correct frames. And what an acknowledgement means is that you'll send a short packet from the receiver back to the sender. This short packet is called an ACK, short for an acknowledgement. The sender, the rules at the sender is simply that you automatically resend the frame if you have not received the ACK after a certain time period. This is called a timeout. So a timeout essentially means that the sender hears no ACK within a certain time bound. If that's the case, the sender will automatically resend. Here we can see how ARQ works. Let's just go through some examples. This is the normal operation case. And this is when no packet loss, no frame loss occurs. And this is a new kind of diagram for us. This is a time sequence diagram. The sender and receiver are both shown as vertical lines. In this diagram, time runs down the page. So I'll trace over the action on the diagram. Two things really happen here. The sender sends a frame to the receiver. There we go. The arrow slopes downwards because sending takes some time, so time passes to send this message across the network. But at any rate, the receiver receives the frame and it sends its own message, an ACK, back to the sender to say, yep, got a good packet there. This ACK is received before the timeout period passes, so the sender doesn't need to resend. Everything's good. The frame has been transferred across the network and no retransmissions are needed. Here's the loss and retransmission case. The frame is sent, something happens, doesn't make it to the receiver correctly. After a certain amount of time passes, the sender says, hey, what's going on here? Something must have gone wrong. And it automatically resends the message to the receiver. This time the message gets through, the receiver sends an ACK back, and I guess that is before another timeout passes. That being the case, both sides are happy. This could go on if the more frames were lost, the sender would repeat again and again and again. Now there are a couple of things we might note about this diagram. First, you might actually wonder how it is that a frame can be lost inside a link. I mean, what happens? Does the signal just get tired and stop propagating? No, the signal continues to propagate. Two things could happen. The frame could make it to the other side, but an error could be detected because some of the bits were corrupted. When this happens, it's normal for the receiver to throw the message away and not take any action because it's uncertain what the correct message is. So this could look like a message disappearing, even though it really reached the receiver. However, it's also possible that the receiver will not even see the message. This could happen if the transmission error is severe enough that, say, the framing was affected. In this case, the receiver might not even find the starter frame, so it might not even detect that there is a frame there. This would look like a frame has been lost inside the network. A second thing to note is you can see why ARQ in the simple form here is normally done by having the sender automatically resend a message. It's difficult for us to have the receiver send a message to the sender saying, hey, could you send that again? Here the receiver doesn't even know that it's missing a message. It didn't hear something, so it's in no position to request it again. Even if it did, the ACK is just another frame. It could get lost, so the sender might not hear the message to resend. So this is ARQ. ARQ looks fairly simple as a mechanism. Once you get it, you just automatically resend. But a funny thing about network protocols is that there can be some quite subtle interactions. And that's also the case with ARQ. We'll find this a lot for network protocols. With ARQ, there are two non-trivial issues that I'm going to talk about. The first is this timeout. What should the value of the timeout be? We've got to pick something. How long should it be? And the second is actually a more serious issue about how to avoid accepting duplicate frames as new frames. If the sender sends three different frames across the network, 1, 2, 3, maybe with some retransmissions, we would like the receiver to receive the same set of frames in the same order, 1, 2, 3. It's no good if the sender sends 3 frames from a higher layer, passes them over the network, and the receiver thinks that 4 frames have in fact been sent across the network. This could really muck with messages if they were transformed in some way as they went across the network. We don't want that to happen. In fact, what we want to happen for ARQ, which we also usually want for many protocols, is we want performance in the common case, right? So performance is linked to the common case, but we want correctness always. No matter whether our performance is good or bad, we want this protocol to be correct. So let's look at these two issues. Timeouts. Okay, well, the value of the timeout is one of these not too big and not too small kind of issues. We don't want it to be too big because if it is too big, we'll sit around twiddling our thumbs for a long time. The link will go idle and we'll be wasting network resources. If it's too small, the ACK will be on its way, but we'll panic a little early and we'll go ahead and resend a packet or a frame. This is also a waste because we could have sent a new frame. Now, coming up with a value for this timeout is fairly easy on a LAN in the case of most links. And that's because for a LAN like a Wi-Fi, there's usually a clear worst case. In the case of Wi-Fi, for instance, you know about how big the network can be, so you can work out the maximum propagation delay. Wi-Fi also has rules that a receiver needs to send an ACK within a certain time period. So we can usually bound pretty well when an ACK will come back. And that's the case for most links. However, timeouts are actually much harder when we're talking about sending across the internet as a whole, and timeouts in the case of AIQ being used at the TCP level. And this is because there's a lot of variation in the amount of time it can take to use a path across the internet. You could be sending next door or to the other side of the world. There can also be variation due to other traffic effects on the internet, so it's very hard to predict. We'll revisit this topic later. For now, we'll mostly ignore timeouts and pick a value that's about right, just to make the performance good. Okay, duplicates is a more thorny issue. Let's see what happens if an ACK is lost. Okay, here's our frame being sent. The ACK comes back, the ACK is lost. What's going to happen? The sender will not see anything, and so after the timeout period, the sender will send the frame again. The receiver will see it and send an ACK. Great, looks good. Except, what happens at the receiver here? We get another frame. The receiver has no real way of knowing what this frame is. Is this a new frame? As far as the receiver knows, it might well be. If that's the case, the sender will think it's sending one frame, the receiver will get two frames, our network has gone astray. Here's that diagram cleaned up. Similarly, what's going to happen if the timeout is early? Here's our frame being sent, our ACK coming back, but just a little late. The timeout goes off here. So we will send the frame again, and the receiver will receive it and send an ACK. Again, what's going on here? As far as the receiver is concerned, we've got another frame here, a second frame. This is probably the next frame. It's a new frame, but it's not because of the spurious timeout. And that diagram's cleaned up. Okay, we need to fix this problem to ensure that the retransmission mechanism is correct. To do this, it turns out that it's required that both frames and acknowledgements carry sequence numbers. These sequence numbers, we're going to check them as part of our protocol at the receiver to make sure that we've got the right frame and the protocol is operating correctly. Now, it turns out that in the protocol I'm showing you, where the sender's only sending a single frame at a time and resending it until it gets through, we only need a flag, a single bit, to indicate two different states or two numbers to distinguish the current frame that's been sent from the next one. That's going to be sufficient. The name of the protocol in this case is called stop and wait. Let's see it in action. So our two states with a single bit, we're just going to call them 0 and 1. We're going to alternate packets and number them 0 and 1, 0 and 1. So here's how it would work. This is a frame, F for frame. We'll call this one 0. So I'm going to get an ACK for that. I'll call that A0. Okay, the sender will now advance to the next frame. It will send F of 1 and will ACK A of 1. You can see here at the receiver, first of all, we get frame 0, and now down here we can see this is frame 1. We have some way to distinguish these two. So here's this cleaned up, and you can see I've added the timeout just to show it's the normal case. Let's look at some of the problematic cases from before. Here's the ACK loss case. So what's going to happen when we have ACK loss? Well, after the timeout, the sender will resend. Now, since it's a resend, it is sending frame 0. The receiver will ACK 0. Here, the receiver received frame 0. Now it is receiving frame 0 again. So the receiver is clear that this is a resend. Yes, got that one right, always comforting. Okay, the other case, a spurious timeout. The timeout goes off a little early. We'll send frame 0. We're going to ACK frame 0. The receiver, here got number 0, and here it can see it is a resend. Wonderful. You'll also note over here, the sender is going to get another ACK for frame 0. Oh, okay, that's fine. I guess that's what it expects since it's sent 2. The sender here does not actually know whether here, this first ACK, it probably thinks this ACK could be in response to the second time it's sent it. It's just got a very short timeout. For all it knows, the first frame was lost and the second frame got through and produced this ACK. It can't really disambiguate these cases, and it doesn't matter. Our protocol is correct in either case, even though the sender and receiver don't necessarily know what's going on. That's all of the subtlety in the design of the system. So here's a cleaned up version of that figure. And now you've seen stop and wait, ARQ, and all of the rules. And this is basically the protocol. This is how it works. And you've seen the different cases. Before we finish, I do want to tell you about one limitation of stop and wait. Stop and wait allows only one frame to be outstanding from the sender at a time. That is, the sender tries to deliver its frame, resending it until it's there before it moves on to the next frame. That is effective for a LAN, and it's used in Wi-Fi, but it's not effective for networks that have a high bandwidth delay product. That's what BD is. Let me just write that. Bandwidth delay. And the reason for this is because with a high bandwidth delay product, many packets could fit on the network at one time, but with stop and wait, we'll only send one. Let's see an example. Here we have a picture of a network where the rate is 1 megabit per second and the delay is 50 megabits per second. That means that the round trip time, or the time taken to send a frame across and receive a reply, is going to be 2D or 100 milliseconds. How many frames could we then send a second? We could send 10 frames a second. And if you imagine a frame is roughly 10,000 bits, that's about 100 kilobits per second. That's not so great considering we've got a megabit per second link, 10 times as fast. What would happen if we raised the bandwidth to 10 megabits per second, the rate of the link? Well, actually, you wouldn't be able to send any faster. With stop and wait, you can only send up to 10 packets a second over this link. So the maximum throughput you can achieve is 100 kilobits per second, no matter how fast the rate is. Wow, that's not so good. The generalization of stop and wait, which handles this problem, is called the sliding window algorithm. The sliding window algorithm allows up to W frames to be outstanding. What we want to do is set W, the number of frames outstanding, to be roughly twice the delay expressed in packets. Twice the delay is also called the RTT, where RTT stands for round trip time. That's a useful thing to know. And if that's the case, as you can see from the figure here, we'll have multiple packets in the network going across and the X coming back, and this traffic will keep the network busy. This is what we will use when we get to the transport layer in TCP, because the bandwidth delay product is higher than it is for most links, like a Wi-Fi. And when we get there, we'll see various options for handling the way we number frames, ACKs, and so forth. But there's no need to go into all of that now. We'll look at that later. And for now, you know how ARQ and retransmissions work with stop and wait.